Welcome to Session 6. Today is a pivot. For the last two sessions, we've been building up the full transformer: encoder, decoder, positional encoding, multi-head attention. Now we strip out the decoder entirely and train only the encoder on its own. What comes out is BERT. And in 2018, it changed NLP overnight. Let's look at exactly what one-directional training costs us. Language model training has one objective: predict the next token. That works beautifully for generation. You feed in the cat sat, and the model predicts on. But to make that prediction legitimate, every position is forbidden from looking to its right. Remember the causal mask from last session? That's the mechanism doing the forbidding. For understanding tasks though, classifying sentiment, resolving a pronoun, answering a question, you want both sides of the word at the same time. Sat means something different in the cat sat, and he sat in judgment, and the word that settles it comes afterwards. Here is that constraint drawn. The sentence is, the cat blank on the mat, and we want the blank. Under the causal rule, only two tokens reach it: the and cat, the two solid red arcs from the left. The three tokens to the right, on the mat, each have a dashed arc with a cross on it. They're present in the sentence, they're informative, and the model isn't allowed to touch them. Before the second row appears, guess how much of the sentence a bidirectional model would get instead? All of it. Same sentence, same missing word, but now every other position reaches the gap, from the left and from the right. Nothing is crossed out. And notice what the two rows differ in: not the architecture, not the sentence, only the rule about which directions are allowed. That one rule is what turns blank on the mat into usable evidence. And when the goal is understanding rather than generating, evidence from both sides is exactly what you want. So, how do you get bidirectional context without breaking the architecture? Here's the key insight. The transformer encoder, the left half of the architecture from last session, has no built-in directionality. Its self-attention can look left and right in equal measure. The causal constraint was never the architecture, it was the training objective. Change the objective, and the constraint disappears. BERT's answer: instead of predicting the next token, corrupt the input and predict the corrupted tokens. Randomly mask 15% of the tokens. Replace them with a special mask placeholder. Train the encoder to reconstruct the originals, using everything around them, left and right. No decoder needed, no left to right rule. In other words, you hand the model a damaged sentence and say, fix it. This bet has a name, a place, and a date. It was made at Google by Jacob Devlin and colleagues in October 2018 in a paper titled BERT Pre-training of Deep Bidirectional Transformers for Language Understanding. BERT itself stands for Bidirectional Encoder Representations from Transformers. The name is literally the method. Their assumption is the one you just saw on the previous slide. The direction problem lives in the training objective, not in the architecture. So, mask the input, predict the gaps, and the bidirectional context the causal mask was blocking should come straight back. And that's enough. A single encoder, trained this way on 3.3 billion words, learns representations so rich that you can fine-tune it on almost any language task. Classification, question answering, named entity recognition, with only a few thousand labeled examples. The bet is that you can front-load all the expensive general learning in pre-training, and then reuse those weights cheaply for any task. Let's see exactly how that masking works, step by step. 15% of the tokens get picked at random, and they're replaced before the input ever reaches the encoder. Let's watch it happen to one sentence. Here's the sentence. The quick brown fox jumped over the fence. 3 tokens are selected: brown, over, and fence, highlighted in gold. The other 5 are left untouched. 8 tokens is a short sentence, so 3 of them is a larger fraction than the real 15%. On a realistic sentence, you would be selecting 2 or 3 words out of 20. This selection happens independently for every training example. Now here's the subtlety. You might be thinking, just replace every selected token with mask and train on that. But if you do, the model learns a shortcut. It only ever needs to predict tokens where it sees mask in the input. And at inference time, real sentences never contain mask. You've built a train test mismatch. Devlin's team fixed it with the 80-10-10 rule, the 3 panels here. 80% of the selected tokens get replaced with mask. That's the core pre-training signal. 10% get replaced with a random word. Over becomes music, which forces the model to build robust representations for every token, rather than only the marked ones. And 10% are left exactly as they were, so the model can never treat mask as a guaranteed signal that a prediction is wanted here. In plain words, the mix is what makes pre-training and deployment look the same to the model. Let's look at the architecture itself. It's almost unchanged from what we built last session. A stack of transformer encoder blocks, multi-head attention, feed-forward sublayer, residual connections, layer norm. The only additions are 2 special tokens and 2 model sizes. Every BERT input begins with a special CLS token, shown in blue, prepended before the first real word. At the end sits SEP, marking the sentence boundary. These tokens carry no linguistic meaning at input time. Their meaning is entirely what the model learns to put in their representations. Above each token, you can see its embedding. And the note on the right tells you what that embedding is: token plus position plus segment, 3 vectors summed. Segment marks which of 2 packed together sentences a token belongs to, sentence A or sentence B. Hold on to that. A few slides from now, BERT is trained on sentence pairs, and this is the vector that tells the 2 apart. Note the position embeddings here are learned, not the fixed sinusoids from last session. BERT never needs positions beyond the 512 tokens it was trained on, so it can afford to learn a free vector per position instead. Those summed embeddings flow up into the stack of encoder blocks. BERT base has 12 layers, 12 attention heads, and 768 dimensional representations. BERT large has 24 layers, 16 heads, and 1024 dimensions. Every layer is bidirectional. There is no causal mask anywhere in this diagram, and that's the whole difference we've been building towards. At the top, every token has an output representation. The CLS token's output, highlighted in gold, is the sentence-level representation, 1 vector standing for the whole input. The other token outputs are what you use for token-level tasks like named entity recognition. 1 encoder, read 2 different ways. So what actually changes between GPT and BERT inside the model? The difference isn't the architecture. Both are built from transformer blocks. The difference is the attention mask, and a mask is literally a matrix, so we can just look at it. Read this grid as the row is the query, the token doing the attending, and the column is the key, the token being attended to. A filled cell means that pair is allowed. Under GPT's causal mask, you get a lower triangle and nothing above the diagonal. The row for SAT reaches CLS, the cat, and itself, and stops. Everything above the diagonal is zeroed out, which is the same fact you saw as crossed out arcs a few slides ago. And here is BERT's. Every cell is active. CLS attends to SAT, SAT attends to SEP, nothing anywhere is blocked. That full connectivity is what makes a bidirectional representation possible. And when you compare the 2 grids side by side, the entire architectural difference between the 2 most famous models of 2018 comes down to which half of a square is filled in. Before we move on, let's put a number on that difference. Here's the question. Take the 6-token sentence you've just been looking at. Under GPT's causal mask, how many query key pairs is the model allowed to use? And under BERT's encoder, how many? Don't estimate it, count the filled cells. There are the 2 grids again, exactly as you saw them. 6 rows, 6 columns, 36 cells in each. We'll walk the causal grid 1 row at a time. And I'll hold back the rows we haven't reached yet, so each one stands on its own. Make your guess before the first row lands. Row 1 is the CLS token asking the question. Under the causal rule, it may look at itself and at nothing else, because there is nothing to its left. 1 filled cell. Row 2 is the. It reaches back to CLS and to itself. 2 cells, so we add a 2. Row 3, cat, reaches 3. You can see the staircase forming now, and you can see why. Each token has exactly 1 more token to its left than the token above it, so each row gets exactly 1 more cell. Row 4, sat. Row 5, on, 5. And row 6, sep, is the only row in the whole grid that sees the entire sentence, 6. So the causal side comes to 1 plus 2 plus 3 plus 4 plus 5 plus 6. and you can see the whole working written out underneath. 21. And BERT's side needs no walk at all, because every row contributes all 6 columns. 6 sixes, 36. So GPT's causal objective may use 21 of the 36 available pairs. BERT's may use all 36. That's 15 extra pairs of context, about 71% more, on a 6-token sentence. And the gap only widens as sentences get longer, since the causal side always loses roughly half the grid. In one sentence, that ratio is the whole reason the benchmark numbers a few slides from now move at all. BERT wasn't trained on masking alone. There was a second objective running alongside masked language modeling. Next sentence prediction. You hand the model 2 sentences packed into one input. CLS, sentence A, SEP, sentence B, SEP, the exact use case that segment embedding on the architecture slide was built for. In this first pair, B really does follow A in the corpus. The man went to the store, then he bought a gallon of milk. The CLS output goes into one small binary head, and that head's only job is to say whether the pair is genuine. Here it says, is next. Now, the negative example, and watch what changes between the 2 rows. Same first sentence. But B has been sampled at random from somewhere else in the corpus. Penguins cannot fly. Nothing connects it to the sentence above, and the head has to say so. Not next. Roughly half of BERT's training pairs were built this way, so the model saw as many fake continuations as real ones. The 2 rows differ in exactly one thing, where sentence B came from, and that one difference is the entire task. And then, a year later, this whole arm was deleted. Roberta, from Facebook in 2019, retrained BERT without next sentence prediction at all, and came out with a better model. Masked language modeling on its own was enough. And you can see why. Trained on long documents, and the model already sees sentence-to-sentence structure inside its own 512 token window. So the extra head was being taught something it was getting for free. Hold on to that when you design a training objective of your own. Next sentence prediction looked reasonable. It shipped in the paper that defined the field for the next 2 years, and it never earned its keep. The only reason anyone found out is that somebody trained the model twice, once with the component and once without, and compared. None of this works without real scale behind it. Here is what went in. 2 corpora. Books corpus, 800 million words of unpublished books, and English Wikipedia, 2.5 billion. The bar is cut at the real ratio, so you can see at a glance that Wikipedia is about 3/4 of the total on its own. 3.3 billion words altogether. And not one of them carries a label. No annotations, no task supervision, nothing but the masked token signal you were counting 2 slides ago. And here is what it cost. Every small square is 1 cloud TPU. BERT Base ran on 16 of them for 4 days. BERT Large on 64, also 4 days. 4 times the block, 4 times the hardware, same wall clock time. You might be wondering whether that was normal for 2018. It was not. This was an industrial scale budget, well beyond what a university lab could put behind a single training run. But you pay it once, and this fan out is the whole bet. Those weights come out of the bottom of the run, and every downstream task, sentiment, entity tagging, answer spans, sentence pair inference, takes the same weights and adds 1 small head, trained on a few thousand labeled examples. The expensive general learning is paid for once and then amortized across every task that will ever use it. That bet paid off so widely it became the default for the field. Every major model since, from Roberta to T5 to GPT-4, follows the same pre-train, then fine-tune template. So how do you actually turn this pre-trained encoder into a working classifier? Fine-tuning is surprisingly simple. You take the pre-trained encoder, attach a small task head to the CLS output, give it a labeled dataset, often just a few thousand examples, and train the whole thing end to end. The heavy lifting was already done during pre-training. Here is the pre-trained encoder processing a sentiment sentence. This film is great. The CLS output at the top, in gold, holds the sentence-level representation, and the 5 gray outputs beside it are the per-token representations we're not using for this task. Before fine-tuning, that gold vector encodes general language properties, grammar, semantics, syntax. It doesn't yet encode sentiment. We attach a single linear layer followed by a softmax. That's the entire task head, the green box. The whole model, BERT plus head, is then fine-tuned together on the labeled sentiment data. And the output here is positive, with probability 0.91. The point is the division of labor. The encoder's pre-trained weights already know grammar and syntax, so the head only has to learn the final mapping from a sentence vector to two labels. That's why a few thousand examples is enough. So, did the bet pay off? It did. In October 2018, BERT set a new state-of-the-art on 11 NLP benchmarks simultaneously. And here's the detail I want you to hold on to. Same pre-trained weights every time, nothing changed but the fine-tuning head. First, the baseline. These gray bars are the prior state-of-the-art on 5 of those benchmarks, the best systems in the world before BERT. GLUE, the composite of 9 language understanding tasks, stood at 72.4. Squad 1.1 question answering was already at 91.0, close to saturated. Squad 2.0 sits far lower, at 75.1, because unlike version 1.1, it also includes questions with no answer anywhere in the passage, so the model has to recognize absence, not just locate a span. Named entity recognition at 91.9, and swag common sense reasoning at 73.2. And before you read the bars, notice the axis starts at 60, not 0, because the interesting range is the top third. Now, BERT large, in blue, 1 bar per benchmark, all from the same pre-trained weights. And you can see it at a glance. Every single bar is taller. Not most of them, every one. And here's the size of each move, measured against the old level. Plus 8.1 on GLUE, plus 2.2 on Squad 1.1, which was already nearly maxed out. Plus 8.0 on Squad 2.0. Plus 0.9 on NER, the one benchmark where the prior system was genuinely hard to beat. And plus 13.1 on swag. You might want to credit scale for all this, but model size and training data volume didn't change relative to the strongest baselines. What changed is that pre-training saw both sides of every token. In one sentence, bidirectionality, not scale, is what bought these numbers. BERT didn't stay alone for long. It sparked an entire generation of encoder-only models, each addressing a different limitation. Here are the 3 you'll meet most often. RoBERTA, robustly optimized BERT, from Facebook in 2019, kept the architecture but changed the training recipe. More data, longer training, larger batches, and it dropped NSP entirely. Exactly the ablation we discussed a few slides earlier. The conclusion: BERT was undertrained. Same architecture, more careful training, substantially better model. Distill BERT came from Hugging Face the same year, and its question was deployment. Knowledge distillation compresses BERT to 60% of the original size, runs 40% faster, and keeps 97% of the performance. That matters because a model you want to run on a phone or in a browser cannot be 340 million parameters. Albert, a light BERT from Google in 2019, went a different direction. Parameter sharing across layers and factorized embedding matrices. 18 times fewer parameters than BERT large, with competitive performance. The insight was that BERT's depth was useful, but its parameter count was wasteful. 3 different answers to 3 different questions. How to train better, how to deploy smaller, how to compress parameters. All 3 are still in widespread use today, and you'll meet one of them again in the lab at the end of this session. But BERT has a real limitation. BERT is an encoder. It reads, it represents, it classifies. It cannot generate. Ask BERT to complete a sentence, write a paragraph, or answer a question in free-form text, and there is no mechanism in it to do so. The decoder, with its causal mask and its token-by-token output, was removed. What is left is understanding without production. Look at the comparison. BERT reads the whole sentence with bidirectional attention, and that's why it excels where the answer is already in the text. Classification, named entity recognition, extractive question answering. The price is that every new task needs its own fine-tuning run. You get no few-shot capability. GPT is the mirror image, strictly left to right, causal attention, and out of that constraint comes what BERT can't do. It generates text naturally, and it can take on a new task from a few examples in the prompt with no gradient steps at all. 2 models, 1 architecture, opposite training objectives, and completely different capabilities. BERT understands, GPT generates. and GPT is where we go next. Let's step back and take stock. 5 sessions in, we started with why language is hard. We gave words coordinates. We learned to process sequences. We broke the bottleneck with attention. And last session, we built the transformer, the architecture that made everything else possible. Today, session 6, we took the encoder half of that transformer and trained it to understand BERT, the first model to show that a single pre-trained encoder could reach state-of-the-art on every major language understanding benchmark at once. 8 sessions left. Session 7 is next, GPT, the other half of the transformer story, decoder-only, autoregressive, and capable of something BERT never attempted, generating language. And if we zoom out, the whole course sorts into 3 phases. Foundations, sessions 1 through 5, the ideas behind every model. Architecture, sessions 6 through 9, BERT and GPT, and what comes after them. And real world, sessions 10 through 14, what it takes to train, deploy, and trust these systems. One more thing before we go. BERT reads everything before answering. Next session, GPT, which reads nothing to the right at all, and uses that constraint to generate text 1 token at a time. That one-directional rule turns out to be the key to language generation and the foundation for every chat model you've ever used. Time to get hands-on. You'll use Hugging Face's Transformers library, the standard tool in the field, to load a pre-trained BERT model and fine-tune it. Part 1. Tokenize a sentence, inspect the token IDs, find the CLS and SEP positions, and extract the CLS hidden state. Look at what that vector holds before any fine-tuning. It encodes general language, not sentiment yet. Part 2. Fine-tune on 1,000 examples from the Stanford Sentiment Tree Bank. Positive and negative movie reviews. Train for 3 epochs and plot validation accuracy. Watch it rise from near random to near state-of-the-art in minutes on a GPU. Part 3. Swap the model. Replace BERT base uncased with distill BERT base uncased. Does the accuracy drop? By how much? Is training faster? You're running your own ablation, the same kind of experiment that produced the BERT family we looked at earlier. The challenge. Visualize the CLS token representation before and after fine-tuning using PCA or TSNE. Plot positive and negative examples separately. Before fine-tuning, they should be mixed. Afterwards, you should see 2 clusters. You might be wondering whether fine-tuning really rewrites the encoder or only the head. This plot is how you find out.